Hello students, welcome to lecture 21 of this course. In the last lecture, we discussed about theory of UV visible spectroscopy, and then we started to discuss applications of UV visible spectroscopy. I will continue with that and discuss more applications of UV visible spectroscopy. As I discussed in the last lecture, there are two very important applications of UV visible spectroscopy, one in qualitative analysis and another is in quantitative analysis. In qualitative analysis, we can do several different things, and one of the most important thing is structural elucidation of organic compounds. When we are going for a structural elucidation of organic compounds, what we look for is the presence or absence of a particular absorption band at a particular wavelength. This band may be regarded as an evidence for the presence or absence of a particular chromophore in the compound. So, just by looking at the band at a particular wavelength, we can tell about whether a particular compound is present in the sample or not. The second important qualitative analysis is in the determination of impurities. So, whenever we are trying to synthesize a molecule or a drug, there is always a chance for different kind of impurities present in the sample. Impurities can be due to reactant or impurities can be due to side product, formation of side products. Again, your reactant and your side product which is present as impurity can have a characteristic wavelength and based on that characteristic wavelength we can tell whether a particular impurity is present or not. So, the different compounds absorb at different wavelength and that can be used for the determination of impurities in a sample. So, first application in qualitative analysis is structure elucidation of organic compounds. So, UV visible spectroscopy is quite often used to look at the different organic compounds synthesized during a reaction. That is why it is generally used for the identification of new drugs and natural products. And as I told you that the useful information about the substance can be obtained by looking at the lambda max and epsilon of the formed product, and based on that we can tell which kind of a structural feature is present in the particular sample. So, a spectrum along with melting and boiling point, refractive index and other properties can be used for characterization of a compound. UV visible spectroscopy is particularly useful in the structural elucidation of organic molecules with conjugated double bond. So, a molecule with a conjugated double bond can be easily be identified using UV visible spectroscopy. Similarly, the presence of heteroatoms can also be identified using UV visible spectroscopy. From the location of peaks and combination of peaks, it can be concluded whether the compound is saturated or unsaturated. whether heteroatoms are present or not, and that is why UV visible spectroscopy is quite often used during the synthesis. So, here is the 3 different aromatic compounds given and their characteristic UV visible spectra is also given. So, this is your naphthalene, this is with the 3 benzene ring and this is with the 4 benzene ring, and you can see that the characteristic spectrum of these 3 compounds are quite different, and that is why UV visible spectroscopy can be used to tell about the structural feature of the compounds. So, here is some example of absorption maxima of some organic compounds. Here first case ethylene, it has a peak around 180 nanometer and its molar absorption coefficient is 10,000. 1,3-butadiene 217 nanometer and epsilon value is 21,000. Vitamin A, it absorbs at 328 nanometer and its epsilon value is 51,000. Beta carotene absorbs at 450 nanometer and its molar absorption coefficient is 1,40,000. Benzene has absorption peak at 255 nanometer and epsilon value is 180. Naphthalene has lambda max at 286 nanometer and its molar absorption coefficient is 360. Anthracene has absorption peak at 375 nanometer and its epsilon value is 7100. Naphthacene has lambda max at 477 nanometer and this is its epsilon value. So, you can see that every compound has different lambda max and different epsilon value. So, based on that we can not only qualitatively say this is the compound, we can also calculate concentration or amount of this compound using epsilon value, and I will go to quantitative analysis in a few minutes. So, but what you need to know is epsilon is very important when we want to get the concentration. So, an absorption band at 254 nanometer with characteristic vibrational fine structure is an evidence for existence of aromatic structure. Other compound can also show their characteristic peaks. For example, cyanocobalamin has characteristic bands at 278 nanometer, 361 nanometer and 550 nanometer, and their absorbance ratio is 2:3:1 respectively. So, based on that you can identify the compound. So, here is another case. For example, if you are looking at phenolphthalein, phenolphthalein is a mixture of 2 different species, benzenoid and quinonoid. One exists at pH 7, another exists at pH 9, and this is colorless and quinonoid is pink, and based on acidic conditions or basic condition one of these form can exist, or in between it can be a mixture, it can be mixture. The lambda max for this compound is in UV region, whereas lambda max for quinonoid is in visible region and its lambda max is 550 to 555 nanometer, whereas for benzenoid lambda max is in UV region. So, looking at the lambda max value, you can identify not only the compound, but you can also identify its different forms, Sometime we can identify a particular compound by converting it into a derivative which is colored. For example, if you take the carbonyl compound, they can be converted into phenyl hydrazone via reaction with 2,4-dinitrophenylhydrazine, 2,4-dinitrophenylhydrazine, and based on its absorbance we can know whether carbonyl functional group is present in the molecule or not. So, this is your 2,4-dinitrophenylhydrazine, and when it reacts with carbonyl compound, it gives you phenyl hydrazone derivative which has orange color and lambda max of 430 to 480 nanometer. So, a compound which does not give color can also be identified, at least its functional group can be identified by reacting with a compound, so that you get a product which has some color. For example, in this case what we are doing is carbonyl compound, taking carbonyl compound and reacting it with 2,4-dinitrophenylhydrazine to get a colored compound which has lambda max of 430 to 480 nanometer. Not only that, we can also differentiate between different geometrical isomers, or we can tell about configuration of geometrical isomers. For example, this is the case of cis stilbene, and when you take a spectra of this compound in hexane, what you will get is this, which has a lambda max around 276 nanometer. Whereas, if you take trans stilbene and try to obtain UV visible spectrum in hexane, what you will get is lambda max around 294 nanometer, So, just by looking at the positions of lambda max, we can differentiate between different geometrical isomers. We can differentiate whether a particular compound is in cis form or in trans form. So, cis stilbene has lambda max of 276 nanometer, whereas trans stilbene has lambda max of 294 nanometer. Distinction in conjugated and non-conjugated compound can be made. For example, here is the two different compounds. Here you see there is conjugation, whereas in this case there is no conjugation. So, if we look at the spectrum of the compound 1 and 2, the N to pi star band for the carbonyl group in the compound 1 will appear at longer wavelength, as it is a alpha beta unsaturated ketone. So, since this keto group is in conjugation with this double bond, and so N to pi star band is going to appear at longer wavelength, whereas in the compound 2 C double bond O, this N to pi star band for this compound is going to be at lower wavelength, since this C double bond O is not in conjugation with double bond, and so the band appears at shorter wavelength. Now, we can also use UV visible spectroscopy to look at which tautomeric form is present. For example, you see the case of this versus this, and so between 2 hydroxypyridine and 2 pyridone, these are the two tautomeric forms, can also be distinguished using UV visible spectroscopy. So, in this case 2 then preference of one structure over the other can be detected by UV visible spectroscopy. So, here you see this lone pair N2 pi star is again in conjugation with this double bond, and so just by looking at this we can know N2 pi star band, we can know which tautomeric form is present in the sample. Now, UV visible spectroscopy can be used for the detection of metals. Here we do not take a spectra of metals, what we do is we convert metal to a complex which absorbs in UV visible region. For example, aluminum can be identified by reacting it with erichrome cyanide R dye at pH 6. What will happen is it will form a pink complex, and it will form a pink complex, and lambda max is going to be 535 nanometer. So, erichrome cyanide R dye is red, and when it reacts with or when it forms complex with aluminum, it gives a pink complex which absorbs at lambda max of 535 nanometer. Similarly, arsenic can be identified by reacting it with zinc. What happens that arsenic reduces to SH3, and this reacts with silver to form red color complex diethyl dithiocarbamate, and it absorbs at lambda max of 535 nanometer. Cadmium on reaction with chloroform solution of dithiazone in presence of NOH gives pink to red complex. So, dithiazone is a pink complex, pink dye. When it reacts with cadmium, it gets converted to red complex, and its lambda max is 518 nanometer. Similarly, chromium 6, it reacts with chloroform solution of dithiazide, and it gives a red violet complex which absorbs as 540 nanometer. Similarly, lead reacts with dithiazine in presence of ammonia to give you cherry red complex which absorbs at 510 nanometer. Mercury on reaction with chloroform solution dithiazone gives you orange complex, and its lambda max is 492 nanometer. Copper reacts with neocuprine in neutral or slightly acidic condition to form yellow complex which absorbs as 457 nanometer. So, just by reacting a particular metal with a dye which color changes when it reacts with metal, and the metal dye complex absorbs at different lambda max, then we can predict the presence of metal in a solution. UV visible spectroscopy can also be used to identify different proteins. It is also quite useful for the proteins that contain prosthetic group, for example, hemes, flavins or carotenoids. So, in that case, when there is a prosthetic group, some metal protein complexes have very strong absorption band in near UV visible range, and these bands are usually sensitive to local environment, and so we can study the changes in protein happening. Here is some prosthetic group and their UV spectrum. So, beta carotene can be in 3 different forms. When it has all trans beta carotene, then you can obtain this kind of a spectrum, whereas if there is 9 cis beta carotene, then you will get this green spectrum, and if you have 15 cis beta carotene, then you have this red spectrum. So, just by looking at the spectra, you can also differentiate between different types of carotene. Heme is a very important prosthetic group, and it is present in few proteins, and those proteins can be characterized by looking at the absorption of this heme group. Particularly Sauret band is quite useful, and that if you look at the Sauret band, and you can tell about the environment around the heme group. UV visible spectroscopy can also be used for detection of impurities, and basically it is one of the best methods for determination of impurities. Additional peaks can be observed which is due to impurities, and then if you compare with the standard raw material, you can tell whether that is impurity or not. You can also measure the absorbance at a specific wavelength, and that can be used to identify impurities. For example, impurity in paracetamol is detected by using UV visible spectroscopy. This is the way in which paracetamol is obtained. So, this is para-aminophenol on acetylation gives you paracetamol, and this is diacetylated paracetamol as a byproduct. So, impurities can be present as a byproduct or can be due to byproduct, and our aim should be to remove that byproduct, and for that it is important to know what is the amount of the side product, and once you purify it, then again you need to make it sure that there is no byproduct left, and for that you have to use UV visible spectroscopy. So, this is your UV spectrum of paracetamol PCM. This is the standard, and if PCM is present with impurity, then these extra peaks will be obtained, and in the final paracetamol or the paracetamol which are going to be used as a medicine, you need to make sure that these peaks are not present, so that there is no impurities. UV visible spectroscopy is quite often used for narcotics and drug testing. Many illegal drugs contain aromatic compounds that produce characteristic UV visible spectrum. For example, these are the few drugs and corresponding lambda max value. Cocaine in 0.2 normal H2SO4 has lambda max around 233 nanometer. Codeine in water has lambda max around 284 nanometer. Morphine has lambda max around 285 nanometer. Nicotine has lambda max around 260 nanometer. Amphetamine in methanol gives you peak at 258 nanometer, and similarly caffeine in 0.2 normal H2SO4 gives you lambda max at 271 nanometer. So, just by looking at this looking at the UV visible spectrum and identifying peak at a particular lambda max, you can tell whether a particular narcotics or drug is present in the sample or not. Ink analysis can also be done using UV visible spectrometer. It is quite often used to investigate the coloring compounds in the pen ink. Ink analysis, as I told you in the second lecture, it is needed to reveal useful information about forgery of a particular question document, and what you try to look at is which kind of pen is used for preparing the question document. For example, these are the 4 different kind of pen, and if you analyze their ink, what you will get is the different spectrum, and each of the spectrum is unique. What does that mean is all the 4 inks used by different pens, for example, Bic or Morrison or Parker or Tesco, has different spectrum, and so you can know which kind of ink is being used to write the document, and just by looking at the ink you can know whether that document is fraud or not. I have told you some example of qualitative analysis. There can be 100 different examples, and if time permits in the later lectures I will discuss more applications, but let us first see and look at other kind of applications of UV visible spectroscopy, and one of the most important application is quantitative analysis. So, UV visible spectroscopy is not only used for qualitative analysis, it is also used for quantitative analysis, and most important hypothesis which we used to analyze the quantity is Beer-Lambert's law, which I have already discussed, and the equation which we are generally concerned with is A is equal to epsilon Cl, where A is absorbance, and you can look at that absorbance is proportional to concentration. Absorbance is proportional to concentration. So, if you have two samples and a particular compound is in both samples at different concentration, you can tell that what is the concentration of that particular compound in sample 1 and what is the concentration of that molecule or that substance in the sample 2 using Beer-Lambert law or Lambert's-Beer law. So, here epsilon is extinction coefficient, C is concentration, and L is the length of the cell that is used in UV spectrophotometer. For example, in the estimation aspirin, impurity from such as salicylic acid and heavy metal ions in ASP tablets can be estimated. Okay, for example, look at this spectrum. This is UV visible spectrum of aspirin and salicylic acid mixture. Aspirin has lambda max at 229 nanometer and salicylic acid has lambda max at 296 nanometer. These two are calibration curve. One for ASP and another for your salicylic acid. One for ASP and other for salicylic acid. And just by using calibration curve, you can know what is the concentration. For example, if absorbance is here and if it goes like this, then you know this is your MR. So, this is for aspirin and this is for salicylic acid, and if I have suppose absorbance at this point, absorbance at 220 nanometer is this, then concentration of your aspirin will be around 18 microgram per ml, and if suppose concentration of salicylic acid is around your this point 0.3, then you have probably the concentration of salicylic acid is around 8 or 9, between 8 and 9. So, just by using calibration curve and measuring the concentration of the sample at the 229 nanometer or 296 nanometer, we can obtain what is the amount of aspirin in that particular sample and what is the amount of salicylic acid in the particular sample. We can also look at drug overdose study. Drug overdose can lead to death. Overdose of drug in person can be studied by UV visible spectroscopy. For example, overdose of aspirin can be studied using UV visible spectrum of blood plasma of a person with overdose of aspirin. Therapeutical level of aspirin are typically 150 to 300 milligram per liter, and for post by operation it is 75 milligram per liter. So, the level of salicylate present in blood plasma can be analyzed using UV visible spectroscopy to indicate if the subject has taken a therapeutic dose or a particular person has taken a therapeutic overdose. The moderate overdose is around 500 to 700 milligram per liter, whereas therapeutic dose is less than 300 milligram per liter, and severe overdose is greater than 750 milligram per liter. And we can calculate the amount of salicylate again using calibration plot, and that will give you salicylate in blood sample. So, these are the few different samples. Black one is aspirin 1, this red one is aspirin 2, this one is your aspirin 3, and this one is aspirin 4, this one is aspirin 5. So, these 5s are used to make a calibration curve, because for them we know the concentration. All for these all we know the concentration. So, this one is unknown, this one is known. So, once we made the calibration curve, then we can measure the concentration of unknown, or we can take the absorbance of the unknown sample, and this is the spectrum of unknown sample. So, just by measuring the absorbance at 527 nanometer and using this calibration curve, we can know what is the amount of aspirin in that sample. We can also calculate the percentage of vitamin A1 and vitamin A2 in natural fats of oils, and that we can do it by measuring the intensities of peak at 325 nanometer and 351 nanometer. Vitamin A1 absorbs at 325 nanometer, whereas vitamin A2 absorbs at 351 nanometer, and that is why by measuring the intensity of peak at 325 nanometer and 351 nanometer, we can know the concentration, or we can know the percentage of vitamin A1 and vitamin A2. Similar process can be used for estimation of ergosterol in fats, anthracene in benzene, carbon disulfide in carbon tetrachloride, and chlorophyll in plant materials. We can also use UV visible spectroscopy to study proteins. There are a lot of things we can do. Some of them we will discuss, and we will see if we have a time, then we can discuss more applications. So, this is your peptide bond. We know that proteins have alpha amino acid attached to each other by a peptide bond, and these are the 3 chromophores, aromatic chromophores, which is present in the protein, apart from the cysteine, which can also act as a chromophore. This 3 amino acid has different characteristic spectrum, and it is shown here. This is for phenylalanine, this is for tyrosine, this is for tryptophan, and this table gives you the lambda max and epsilon max value. So, tryptophan absorbs at 280 nanometer and has epsilon max, and it is around 5600 per molar per centimeter. Tyrosine 275 nanometer. So, this is basically epsilon at lambda max, and phenylalanine absorbs at 258 nanometer, and this is epsilon max value. So, we can also use your, let me go back again, we can measure the protein concentration by measuring the absorbance at 280 nanometer. So, every protein has characteristic epsilon value, because of presence of tryptophan, tyrosine or phenylalanine, and since your epsilon value of tryptophan is quite high. So, tryptophan absorbance is measured to know the concentration of protein. The tryptophan absorbs at 280 nanometer, and so we measure the absorbance at 280 nanometer, and then by using epsilon we can calculate what is the concentration of protein in the sample. There are other methods, spectroscopic methods for determination of protein concentration, and they are based on your combining your protein with a dye which can give you color in visible region. So, this is BCM method. There is a biuret method, Lowry method, Bradford method, and then a spectrophotometric method A280 by 260 can be used to know the concentration of protein in the sample. And the choice of method depends on the particular sample. It will depend on sensitivity required and the presence of interfering substances and time available for the assay. So, these are the different methods, biuret method, Lowry method, Bradford, BCA method and spectrophotometric method, and this is your sensitivity, low, high, moderate. This takes 20 to 30 minutes, this takes 40 to 60 minutes. So, these are the different time required. Here reagent is alkaline copper sulphate, here reagent is copper plus Folin CuSl2 reagent, Comasi brilliant blue is used in Bradford method, and this is copper plus this dye is used for BCA method. So, as I told you, quantification of nucleic acid and protein can be done, and this is your the different spectrum of DNA protein and DNA protein. So, this is for protein, this is for DNA, and this is for protein DNA mixture. And just by looking at 280 nanometer by, if you remember, 2 absorbance at 280 divided by 8 to 60, we can know what is the amount of nucleic acid and protein in the sample. Nucleic acid and protein in the sample. So, this is a spectra of protein, and you can see that there is a peak around 280 nanometer which is due to tryptophan, and this is for DNA molecule. And now, if a mixture has both DNA and protein, then what we do is we get this ratio, and that can tell you about the protein DNA ratio. So, here is the different colorimetric methods for determination of protein concentration, and I told you one of the methods is Bradford assay. In Bradford assay, protein reacts with Bradford reagent, this is Bradford reagent, this is Comasi G250, which absorbance is at 465 nanometer, and when you add this dye to the protein, it forms a protein dye complex which is blue in color, and it absorbs at 595 nanometer. So, just by looking at the absorbance at 595 nanometer, you can calculate what is the amount of protein in the sample. For Lowry test, what we do is first protein reacts with copper 2 plus in presence of OH minus, and then this complex Folin CuCl2, this is a dye which gives you a blue color, blue protein complex, and just by measuring the absorbance of this protein complex at 660 nanometer, we can know what is the concentration of protein. The next one is BCA test, and again in this copper 2 plus and BCA is used to get this complex, colored complex, which absorbs at 562 nanometer, and just by measuring the absorbance at 562 nanometer, we can know the concentration of the protein in the sample. The UV visible spectroscopy is not only used for the measurement of concentration, it can be used to study the cell viability. For example, this MTT assay, which is well known viability assay done in lot of biochemistry labs. Here MTT in presence of NADH or NADPH gives you pharma-Jan dye, and this absorbs at a particular wavelength. So, by looking at the formation of this dye, we can know whether cell is viable or not. If cell is not viable, then NADP will not be converted to NADH, NADPH, and then your MTT will not go to Farmason dye, and if it is going to Farmason dye, then you know that cell is viable. If not, then cell is not viable. So, this is quite often used to study the cell viability assay. There are other techniques of cell viability which again uses dye to get a complex which can be detected either by UV visible spectroscopy or by fluorescence. For example, you see we have already discussed about MTT going to MTT Farmason dye. Similarly, luciferase activity can be checked. WST8, which is a colorless substrate, but in presence of NADH, NADPH, it goes to this WST8 Farmason dye. The scalcin AM is non-fluorescent compounds when it is acted by esterase, which basically hydrolyze this calcin AM. Calcin is formed which has a different color and lambda max value. So, this kind of studies can be done if you want to look at whether cell is viable or not. Similarly, we can also look at the SOD1 activity test. So, in this hematoxylin goes to hematine when autooxidations happens. Autooxidations happens, then hematoxylin goes to hematine. What SOD1 does it is inhibits this process. So, if SOD1 is active, then it will bring hematine back to hematoxylin, and percentage inhibition can be obtained by measuring the absorbance at 560 nanometer, and that can tell you about SOD activity. Similarly, lipid peroxidation assay is quite often done, and for that what we do is we can look at the lipid peroxidation. When lipid peroxidation happens, hydroxynonenal and melanoaldehyde is formed. When they react with diindolylalkane, then a complex is formed, a product is formed, and its amount can be detected by measuring OD at 586 nanometer. Apart from that, microbial growth kinetics can also be studied. We generally use UV visible spectrophotometer for that. Here the underlying principle is not absorbance, it is scattering, and since scattering also does not let light reach the detector, and so what happens that absorbance increases if there is a scattering of light, and by looking at how absorbance changes, we can talk about how much turbidity is formed. So, when number of microbial cells increase in culture, they cause more scattering in light, and the detector therefore receives less amount of radiation, and that is recorded as higher absorbance, and this is the picture. You can see in blank it is at 0, and when there is cell formation or increase in the cell, then what happens that it scatters the light and less light reaches a detector, and you see higher absorbance. This higher absorbance can be measured at 600 nanometer, and that is generally called the turbidity assay, generally known as turbidity assay, which is done at 600 nanometer, and just by looking at you can also talk about microbial growth. Similarly, optical band gap identification also can be done using the UV visible spectroscopy. The measurement of band gap of materials is important in semiconductor, nanomaterial and solar industry. Band gap basically refers the gap between valence band and conduction band. This I have already told to you, and you can look at the UV visible spectrum of, for example, TiO2 molecule. Just by looking at that, you can tell what is the band gap. So, these are the few applications, and there can be more application, but since now time is up. So, I will stop here. I will discuss some more application in the next class, and then I will move to fluorescence spectroscopy. Thank you very much. Thank you for listening. See you in the next lecture. Bye.